Hi everyone! Today we're doing notes for 6.5 graphs of exponential models. The graph of a growth function rapidly goes up to the right, while decay functions drop quickly and then level out to the right. If the base of the function is greater than 1, then the function is a growth function. So again, if the base is greater than 1, then the function is a growth function. So we can see this here. Our base is b. If it's greater than 1, we have growth. And that shape is it's going up from left to right. If the base is greater than 0 but less than 1, then we say the function is decaying. So again, if the base is greater than 0 but less than 1, then we say the function is decaying. So you can see here b is between 0 and 1, and that's decay, where our graph is going down from left to right. Although in an exponential function, the constant a in the function f of x equals a times b to the x can be either positive or negative. In many applications, a represents the initial amount of some quantity, like the initial number of bacteria, the initial amount of an investment, the initial number of animals in a certain region, etc. In these cases, a is greater than 0. For the following functions, we have to identify the values of a and b and compare the graphs of these functions. So, as we remember, our functions are always of the form f of x equals a times b to the x power, where a is always our starting value and b is our multiplier. So for the first graph, we have that our starting value is 3, and our b, our multiplier, is 2. If we look at the second graph, we can see that our starting value, is 4, and our b, our multiplier, is 1/2. In both of the cases above, a is greater than 0. We can see in the first graph where b is greater than 1, the graph was increasing. And the second graph where b is between 0 and 1, the graph was decreasing. All right, so a couple definitions. If it's growing exponentially, this is if we're given an exponential function, f of x equals a times b to the x power, where a is greater than 0. If b is greater than 1, then the function is said to grow exponentially. Decays exponentially gives an exponential function, f of x equals a times b to the x power, where a is greater than 0, and b is between 0 and 1, then the function is said to decay exponentially. So we're going to use the graph of the exponential function to answer the following. First, we have to make an input-output table with the given ordered pairs and continue the pattern. So first, we're given x is 0 and f of x is 3. That's our y-intercept, or our starting value. We also see that we have the point 1, 6. So if I look at the relationship here, x is increasing by 1. F of x, I'm multiplying by 2. So if I continue the table, my x values will go 0, 1, 2, 3, 4. And then for my f of x values, we'll continue this pattern of multiplying by 2. So I'll have 12, and then 24, and 48. To write an equation, we have f of x equals our starting value, a, which is our y-intercept, so 3, times our multiplier, which is 2, raised to the x power. So if we evaluate each of the following, f of 1, the value of the function at 1, we can see that right here is 6. Oops. F of 2, the value of the function at 2, you can see right here, it's 12. If I want f of blank equals 3, I'm looking where my output is 3. So we can see here my output is 3 when my x is 0. That's our starting value. And last, f of blank equals 12. Well, we did that one earlier. If the output is 12, the input is 2. Okay, here's another one. We're going to use the graph of the exponential function g to answer the following questions. So again, we're making an input-output table. So I have this initial value, 0, 2, our y-intercept. And next we have the point 1, 8. So you can see here we have a multiplier of 4. So if I continue the pattern for my x values, I have 0, 1, I'm going to add 2 and 3. And then if we continue our pattern of multiplying by 4, 8 times 4 gives us 32. And 32 times 4 will give us 128. So if we're writing the equation, we have a function g this time. So I'm going to say g of x equals our initial value, 2, times our multiplier, 4, to the x power. If we evaluate the following, g of 0, the value of the function at 0 is 2. G of 2 equals, we can see 32. G of blank equals 8. If I look at my table, when g of x is 8, that means my x is 1. And the last one, g of blank equals 128. Again, my output's 128, so if I look, my input x is 3 for that value. Okay. Last, when graphing an exponential function, you will need to identify 3 points on the graph and draw a smooth curve to connect them. An easy choice to use is, now remember, our function always looks like f of x equals a times b to the x power. So a is our initial value, so we'll always have the point 0, a. And then for 1, I'm doing a times b to the first power, which is a times b. For -1, I'm doing a times b to the negative first power, which is the same as doing a divided by b. So let's make a table of values using these and then graph the function. So first I have y equals 4 times 2 to the x power. So 0, 4 will be my y-intercept. To get my value at -1, I do a divided by b. Remember, my a is 4, my b is 2. So 4 divided by 2 is 2. To get my value at 1, I multiply a times b. 4 times 2 is 8. So if I graph this one, I have the point -1, 2. The point 0, 4, and 1, 8. And so from these 3 points, I can draw my exponential function. For our next graph, we have y equals 4 times 1/2 to the x power. So my a is 4, my b is 1/2. So my initial value at 0, my y-intercept is going to be 0, 4. For 1, I'm doing a times b. 4 times 1/2 is 2. For -1, I'm doing a divided by b. So 4 divided by 1/2, which is the same as 4 times 2, which is 8. So if I graph this, I have -1, 8, 0, 4, and 1, 2. And then I connect these and I can see my exponential function. Now, if you notice, my b value, I have 2 and 1/2, which are reciprocals. So you'll notice the values at -1 and 1 switch. When my b is 2, we have exponential growth. When my b is 1/2, we have exponential decay. And so these graphs are almost mirror images of each other, just flipped around the y-axis. And that's all we have for today.